Yes, so please go ahead.
Okay, so I will be sharing my screen. Can you see it?
Yes,
Okay.
I confirm that. I can see that, yes.
That's cool. So I'm Niccolo Gentile. I'm a doctoral student in my last year in economics, working at the Department of Behavioral and Cognitive Sciences. I'm working under the supervision of Professor Conchita D'Ambrosio of the same department, Professor Alexander Kachenko of the Department of Physics and Material Sciences, and Professor Andrew Clark of the Paris School of Economics. And the topic of my research is understanding, so predicting and interpreting the determinants of well-being using machine learning techniques, in particular interpretable machine learning. So yes, so a quick introduction to how the presentation will be structured. We'll be first introducing a bit the research topic, subjective well-being, which I think can be of interest of anyone independently from the field of research we work in. Then I would like to make a bit of a discussion about the trade-off, in a sense, and between predictive accuracy and interpretability, and some of the data associated issues that I've been facing throughout my work. Then I will be focusing more my discussion on random forests, which are, I would say, the algorithm most of interest for my case, and model-agnostic interpretative tools. And finally, I will be introducing the research findings and making a comparison between different interpretative tools. So I would also say that I'm part of DSC-WELL, the Data Science Economics of Wellbeing research project funded by the Institute for Advanced Studies that, as you may have inferred by my supervisor, tries to bind machine learning approaches mostly based on what is done in physics to the research of well-being. And what is well-being? Well-being can be measured as life satisfaction, happiness, or other general indices of psychological functioning. For our project, we focus in particular on subjective well-being, which we will interchangeably call life satisfaction. And in particular, what is done is that people are invited to participate in surveys. And one of the questions in these surveys is simply ticking a box from 0 to 10, where 0 means completely dissatisfied and 10 means completely satisfied. Now, as you can see from how the question is structured, and this is an issue we'll come back later, the question tries to assess life satisfaction in the most objective manner possible, in the sense that for how the question is related to how do you feel in general in life, trying to exclude momentary effects. So whether you feel suddenly dissatisfied because, I don't know, you might have received a speeding tickets before coming to participate in the survey, and this might have an impact on your perceived life satisfaction in this moment. So the question tried to say, in general in life, given your conditions in general. Now, I will also go through some of the findings currently in the literature, and one is this. One is that we tend to prefer to both be rich, and in particular richer than our peers. In the literature, it's found that unemployment harms, not only via the clear channel of reducing the income and in general the possibility of acquiring goods, but also by itself. We find that in general, for people that are older than 30 years old, we observe that married people tend to be more satisfied with their lives. We found also that happiness and life satisfaction are positively correlated with both mental and physical health, whereas the relationship is more ambiguous when we talk about education. This could be either because education is mediated by other variables like indeed unemployment, wealth, and income, but at the same time also because there is investigation going on whether the tendency for someone to be more or less educated has also an impact on how, let's say, the determinant of what makes people desire to pursue more or less educations are themselves related with subjective well-being. In the literature, it's also found that women tend to report higher level of life satisfaction despite reporting higher level of stress, and this is the findings we will come back later. And finally, we found that the relationship between subjective well-being and age is U-shaped, in the sense that people up to their teenage, let's say, tend to be happy with their life. Then there is a bit of a drop, and finally this drop is completely filled in old age. However, there are some recent findings clearly associated with the COVID pandemics and the restriction that are finding that this relation is starting to be a bit more blurred, in the sense that also teenage tend to have lower level of life satisfaction. And this is because, for instance, there is a recent article in The Economist that claims that restriction at a psychological point of view has been particularly harmful for teenagers rather than for older people. Which kind of data do we use? Well, I'm working on the British, my main reference data set so far has been the British cohort study. This is a data set that was started in 1970, following the lives of around 17,000 people that were born in England, Scotland, and Wales in a single week of 1970. And these people were interviewed every 4 years. Up to the age of 16, the parents were replying to the questions for their children. After the age of 16, so starting from 20, individuals start replying by themselves. Then we have the German socioeconomic panel, that is a longitudinal survey of approximately 11,000 private households. We have the Länder in the Federal Republic of Germany were followed from 1984, whereas from the people in the German, Eastern German Länder from 1990. The characteristic here is that, first of all, the data sets are collected yearly. And second is that in a given year, we have people of different ages. In other words, we are not following people that were all born in a given moment, but rather people who were born in different moments, basically, since they can have different ages in a given year. And finally, two new additional data sets I'm working on with colleagues from the London School of Economics and Oxford are the UK Household Longitudinal Study and the Gallup data set. One difference, for instance, is in the former, life satisfaction is measured on a scale from 0 to 7 rather than 10, which can lead to some differences. And the Gallup datasets includes data from multiple countries. So I'm working with these colleagues and we are doing some interesting new findings. So when it comes to the variables we use, the features, I will be using the two terms interchangeably. We started considering the adult variables that were used in a work from Layard et al., a seminal work on life satisfaction, a work from 2014. And these 8 variables are, for instance, the log of the income, the household disposable income per OECD adult equivalent, which is a way to adjust for the number of people in the house, in particular giving less weight to children rather than to adults, because the idea is that you want to actually compute the purchasing power of a family rather than the simple income. And the reason why we take log is because we expect a concave relationship, in the sense that up to a certain point, income doesn't make you any more marginally happy, or very slightly. Then we have educational achievement, which can have 6 distinct values. Then we have a dummy for people who are not unemployed or not. Then there is a variable has a partner that can have 4 distinct values for people who are married or not, with and without children. Then there is a variable called good conduct, which basically means how many times you have been cautioned at a police station during 18 years from when you were 16 to 34. Then we have a variable called physical health that is cardinal for the number of chronic health conditions. As you can imagine, since we're talking about individuals for 34, this is a variable that luckily it's 80% of the time zeros. Then we have emotional health, that is a variable derived from a sum of 24 questions, that tries to assess, for instance, level of stresses, both actually making questions related to your level of stress, as well as questions about lighter physical conditions, like do you often have headache, do you often have backache, do you feel sometimes itchy, that can be all physical manifestation of stress. And finally, a variable for gender, 1 if woman, 0 otherwise. So far in the data, we only have binary genders. Then on top of these 8 variables, we had adding new ones. And for instance, we had new family features that were the number of people in the household, number of natural and non-natural children, whether the parents of the interviewed person were alive, and the new variable called marital status, which replaced has a partner because it is more granular. rather than just being married or not. We are talking about whether they are married, cohabiting, single, separated, divorced, widowed. So we have more levels. And then we have more wealth features. So no longer only income, but we also have the size of the household in terms of rooms, the type of accommodation, whether we're talking about apartments, houses, or even bungalows, and the tenure status, whether you're an owner with mortgage, renting, squatting, or just living rent-free. Now, at this point, I would like to introduce some of the limitations associated with working with this kind of data. In particular, we'll be talking about three main limitations. And one is something we're all familiar with, that is the issue of data availability, clearly controlling the bias-variance trade-off and the problem of overfitting. Now, in terms of data, I built two data sets. One that we call original, including only the 8 variables that were used that I described initially, that were used by Layard and colleagues. And another one that we call extended, where we took 5 of the variables from Layard, and then we added new variables that, using one-hot encoding, in other words, taking categorical variable and splitting them in dummies, led to 97 possible variables. However, what is interesting here is the number of individuals, so the number of observations. Both datasets, we had 8,867 individuals, of which using 80% of individuals in the training set led to a bit more than 7,000 individuals in the training set, which begs the question, do we have enough data to fit and predict with algorithms that have low bias and high variance? In other words, given that the bias is somehow an asymptotic property, do we have enough data to actually model it? And to explain better this point, I would be quoting a paper that, even if you are already expert in the discipline, I strongly recommend, a high bias, low variance introduction to machine learning for physicists. And the idea is simple, is that a simple sample sizes noise can create fluctuations in the data that look like genuine patterns. The advantage here of simple models like linear functions is that since they are incapable of representing complicated patterns, they would ignore, therefore, these noise-induced fluctuations, whereas complex models would model them. And in this case, the models can be tricked into thinking that the noise encodes your information, the well-known problem of overfitting, against which you can guard in two manners, either using less expressive models with fewer parameters or collecting more data so that the component of fluctuations that is associated to noise will smooth out and what will remain is only the genuine pattern. Then the other issue that we have is that we still need models that are interpretable. And there is a trade-off between accuracy and interpretability. So before going into that, what do we mean with interpretability? And I found these 3 definitions that I think are self-explanatory. Kim et al. Refers to interpretability as the degree to which a human can consistently predict the model's results. If you think, for instance, in terms of an estimated linear regressions, if you know that there are 10 variables and you know the values of all the 10 estimated coefficients, once you have a new test individuals, you can exactly predict what will be the dependent variable for this new individual. Then for James et al., we have that interpretability refers to the difficulty to understand how an individual predictor is associated with the response. Once again, sticking to, for instance, linear regressions, this basically refers to the interpretability of in terms of marginal effects of coefficients. And finally, a broader definition by Miller refers to interpretability as the degree to which a human can understand the cause of a decision. And this is, for instance, the case when you have a decision tree. Tito. And so we can make a distinction between so-called inflexible methods that are methods with high bias, low bias, and more prone to underfitting, like linear regressions, that tend to be more interpretable. And on the other hand, we have flexible methods that are the exact opposite and tend to be less interpretable. This is a chart from Introduction to Statistical Learning by James et al. 2013, which perfectly summarizes this trade-off. And in particular, for instance, we have that penalized least squares like last one tend to be even more interpretable because some of the coefficients are shrunk to 0, so only the proper variables that are doing the work in a certain sense remains there. So it's even better to interpret them by overall smoothing multicollinearity in a sense. Whereas on the other opposite end of the spectrum, we have kernel-based methods and ensembles, either via boosting or either via non-parametrically bootstrapping. So, and finally, the third major challenge I didn't deep dive too much into is that of the irreducible error. In other words, this is the variance of the error component that explains the possibility, that encompasses, say, the role of measurement error in dependent variables. Like, for instance, what I was saying initially, the difference between the real people's life satisfaction and what they report, or the omitted variable issue. So basically the not including of predictors, which we assume that all the omitted variables smooth out to zero on average, but we have, this is not in a deterministic manner, and therefore we have a variance around that. And for instance, this is what Oparin et al. Referred to in a work of 2021 talking about latent life satisfaction. Then the issue of dataset size. In surveys, we can have tens of thousands of individuals. In each year, in SOAP, you can reach about 30,000 individuals, but still not millions, but still not millions. And finally, the issue of interpretability. This is because in economic research, whenever we do empirical research, the goal is that of having policy implications. The idea is that a paper should be read or explained to some politicians so that you can tell them, invest in this rather than this if you want to improve life satisfaction, but do this rather than that if you want to achieve this goal. And with few exceptions, therefore, it is strictly necessary to have a clear understanding of the relationship between the variables and the dependent variable. And so given DC3, how can machine learning algorithms beyond linear models be of any interest? Well, for the first issue, one problem with linear methods is that when you introduce too many variables, you can easily go into the issue of harmful multicollinearity. In other words, regressors tend to be linearly correlated, maybe even in a spurious manner, which therefore inflates the standard deviation of the coefficients, leads to many p-value not being too high p-value, so to not reject the null hypothesis of no relation between the independent and dependent variable, and sometimes even possibly harm perfectly multicollinearity, which makes the estimation of least squares coefficients not feasible at all. And this is totally not a problem in machine learning. And we know that introducing more variables can reduce the issue of overfitting, of omitted variables. Regarding the data size, it is true that we do not have millions of data, but the first question is, how big is big? Because we can all agree that if we have billions of observations, this is big data. But 10,000 observation is actually that small, or is actually already sufficiently large to fit nonlinear methods? And this is a question of particular interest, since on average, what you observe in the literature is that linear models lead to R-squares that can be 0.20, so anyway, not particularly high, which makes the question of still trying nonlinear, non-parametric models. And finally, in terms of interpretability, what I was referring before is so-called intrinsic interpretability of a method. So linear regression is intrinsically interpretable. Upon fitting, you already can interpret the methods. But there are post hoc methods that are, the idea is that after fitting the model, you run additional algorithms in order to open the black box and to interpret what are the findings. And this is the field of interpretable machine learning, referring to methods and models that make the behaviors and predictions of machine learning systems understandable to humans. And my recommendation here is a book by Molnar called Interpretable Machine Learning, which is, for me, a must read. And these methods are called model-agnostic interpretative tools, model-agnostic because they can apply to multiple algorithms. So at this point, I think it's important to put some numbers on all the discussion. And the baseline has to be unpenalized linear regressions, because as we said, this is the least flexible algorithms. It has no hyperparameters to tune. It runs in a matter of milliseconds, and it is the most interpretable. So my take for the rest of my career will always be to start a predictive task using linear methods or logistic, if we are doing classification. And what we do is on the data that we have, the British cohort study, we create 100 trained test splits, and we compute the average trained mean square error and the average test mean square error. And these are the numbers that you can see for the original model with only 8 variables, and the extended with 21 variables, 97 splitting the categorical variables in dummies. And as we can observe, adding more variables increased the predictive power by reducing the test mean square error of a bit more than 5%. And as expected, however, we observe no evidences of overfitting, which is proved by the overall comparability of the average trend mean square error and the average test mean square error. What observed in parentheses are the standard deviations. So how do the train test mean square error change across the 110 test split? And overall, they are significantly smaller with respect to the actual value, which is telling us that overall across all splits, we observe similar train and test mean square errors. Now, multiple machine learning algorithms have been fit and used to make prediction, overall leading all to similar generalization losses, similar average test mean square error. Hence, for the sake of this presentation, since also relevant for this topic of interpretability, I will be focusing mostly on random forest. And these are the values for the two derived data sets. And what we can observe is that in this case, the issue of overfitting is a bit higher, in particular in the extended case. I've been running multiple experiments working on a large array of hyperparameters. And what we can observe overall is that there is slight evidences of overfitting, but also what to observe is the similar train and test average mean square error with respect to linear models, which is evidence of either actual linearity of life satisfaction in the parameters, or the issue that I was describing enough, simply sufficient sample sizes to model anything beyond linearity. At this point, the question, okay, but now we know that this model performs similarly. Is there any new information that we can take from random forest? And in doing this, so for linear regressions, it's straightforward. We have the estimated coefficients. And I can tell you that standardizing the variables, so using the coefficients as measures of how much they influence the variance of life satisfaction, the ranking is that the most important variables are those associated with marital status, emotional health, and in third position in linear models, gender. So in other words, whether being a woman or not. On the other hand, to interpret random forest, since it is not intrinsically interpretable, we use free model-agnostic tools: feature importance, permutation feature importance, and Shapley values, in particular computing the mean absolute. I will now go through the three, discussing a bit the differences. So feature importances are computed as the mean and standard deviation of the accumulation of the impurity degrees, in this case, residual sum of square, within each tree. Now, if you have familiarity with regression trees, you know that at each node, the algorithm picks a random subset of variables, and using these variables, split the feature space into two derived sets. So in other words, for instance, if the splitting variable is income, the algorithm may consider on the one hand all individuals that have an income greater or equal to 10,000 pounds, and on the other hand, all individuals whose income is strictly smaller than 10,000. It goes in the two derived nodes, it computes the residual sum of squares, and it does this work with multiple variables and multiple cutoff points, and looks for the one that minimizing the combination of variables and cutoff points, that minimizing the sum of the two residual sum of squares computed into derived nodes. Now, how then is feature importance computed? What we do is basically averaging across all tree. We check in each tree for each point in which the variable xj, for which we are computing the importance, was considered to perform the split. We then take the proportion of individuals that have arrived at that split point, and we use it as a weight for the residual sum of square derived on the 2 points. So this is how feature importance is computed. So this is summarizing equation 2, basically. Now, there is one key clear limitation with this measure, is that feature importance is sensitive to the cardinality of the variables, namely how many unique values such variables can assume. And the reason is that namely high cardinality variables tend to be picked more often to perform the split by the algorithm. This is intuitive because, for instance, If you once again think of gender and income, when it comes to gender, you only have one split point possible, and you constitute residual sum of square on the two deriving nodes. Whereas if you have income, you have possibly 10,000 different values, cutoff points, on which separate the variable space and compute the residual sum of square in the two nodes. So by chance, it will happen that this kind of variable inevitably will lead to a smaller residual sum of square on the two derived nodes, simply because it gives more opportunity to do so, showing more cutoff points. And this has, since feature importance is monotonically increasing in the number of times a variable is chosen to perform the split, this usually is a very bad measure. For instance, in scikit-learn documentation, you can find funny experiments. They use the classic empty cars datasets, they run a random forest, compute feature importance, then they add a completely nonsensical variables randomly creating from a normal centered on something with a given variance, but however has the only property of being perfectly continuous, and it becomes the second most feature important variable. So this is a very bad measure. And this issue, so I will not even present results here related with my research. And what instead we compute and solve these issues is permutation feature importance. This is Tito from scikit-learn documentation. The idea is simple. You take a variable, you shuffle it, and you compute the test mean square error when the variable is as it should be, so with its real values, minus the test mean square error. So sorry, in this case is the contrary, because the test mean square error with the shuffled variable would be higher. You compute the differences in the two test mean square error, you do the operation multiple times and with different permutation, and you compute on average how much the test mean square error changes because that variable was included or not via permutation. And as we can see here, these are the 15 most permutation important variable. The first thing to notice is that indeed the ranking is no longer monotonically in the variable's cardinality. For instance, we have that a variable like log income that is continuous by definition, it's fourth most in permutation important, whereas the second is a simple dummy variable, whether health limits everyday activities or not, yes or no. And anyway, instead, we also have perfectly continuous variables like the number of natural children in the house or number of people that are overall low in the ranking. And the most important variables anyway remain marital status in the first position and emotional health. Whereas it's interesting to notice that female, that so being a woman or not, that as I said, as a coefficients were the third largest for absolute value, here it's only the 14th most important variable. Finally, the last interpretative tool we'll be using are Shapley values. Shapley values are a solution concept from cooperative game theory, theorized by Lloyd Shapley in 1951 and formalized by himself 2 years later. And the idea in cooperative game theory is that you want, after that a game is finished and the achievement has been obtained, you want to share it in a fair manner between the players that cooperated, depending on their efforts. This idea was adapted to machine learning, and the game here is the predictive task, and the achievement is the difference that you obtain between the prediction, including or not a variable. In other words, the average of all marginal contribution across all possible coalition of exploratory variables. Now, here I will not go too much into details of the particular way to fit this method that is called SHAP, that is an algorithm developed by Lumberg et al. 2018, because the idea of Shapley values is that you want to see the marginal contribution of the variables across all possible coalitions of variables. And if you have k variables, you have possible 2 to the k variable number of coalitions to consider, and this would make the computations impossible. Using SHAP, the computational complexity becomes simply squared in the maximal depth of each tree. I remind to both the paper by Lumberg et al. 2018 and the book by Molnar for a better discussion on this. And here I will put it formally. So define xi(xk) as the set of all the possible values of the k variables considered for individual I. And let S be the coalitions of possible features. So basically an F being a value function that maps to the 2 to the k minus 1 possible coalitions to a value function. So in other words, what we're predicting. Now, the Shapley values, how is computed. So Across all possible collisions, we compute the difference in the predicted value of life satisfaction, the terms in square bracket, including or not the variable we are computing life satisfaction over. So for instance, if we have three variables, say emotional health, income, and gender, and we want to compute the Shapley values associated with gender, we will have four possible collisions: both mental health and income, none of the two, only mental health, only income. What we will do is we will consider the collision with both of them, and we compute life satisfaction for this collision, including or not gender. Then we consider the collision without both of them, so with no variables, and we compute life satisfaction, including or not gender. Then we consider only the collision with mental health. We compute life satisfaction, including or not gender. And finally, the fourth collision, 2 to the k minus 1, in this case 2 to the 3 minus 1, including or with mental health, including or not life satisfaction. And this is the term in square brackets. Now, the clear idea is that not all collisions are created similar, because the difference becomes less important in larger collisions. Because if you have already a lot of variables, a change, including or not of variables, can be explained mostly by other variables. Whereas if you have a large change between life satisfaction, including or not, for instance, gender, when you have neither mental health or income, this means that gender makes a lot of is very important. And this is the term that you see at the, let's say, the initial part of the summation of equation 3 that is waiting for the size of the collision. Then what we do is that we take the absolute values of these Shapley values, and so moving to equation 4, we take the absolute values and we compute the mean absolute average Shapley value across all the training individuals, so 1 over n train k. And what we do is that we repeat this operation over the 100 different train test splits. So what we have is the average mean absolute Shapley values. And this is what you can see here. So what we are seeing here is that marital status has computed over the 100 train test splits as the largest mean absolute Shapley values. In other words, across all the possible collisions of variables, here we're talking 21 variables, including or not the value of marital status, so your marital status changes life satisfaction the most. And then the ranking goes for emotional status, tenure status, and whether health limits everyday activities. And as you can notice here, this ranking is very similar to permutation importance, although the two measures are saying something slightly different. What is particularly interesting of Shapley values is rather than looking at absolute values, let's look at their actual values. So here we are not averaging anymore across 100 training test sets, but rather only on the first one without loss of generality. What you are seeing here are the Shapley values as in equation 3 without the absolute values. So for instance, consider a variable like emotional health. The red dots are the Shapley values associated with high levels of emotional health, whereas blue dots are the Shapley values associated with low levels of emotional health. What you are seeing in this graph is that associated with high values of emotional health, there are high positive Shapley values. In other words, when including or not the information that you have, a good level of emotion, the notion of having a good emotional health by itself increases life satisfaction or not a lot, and vice versa. This is particularly interesting as a finding if you consider whether health limits everyday activities. And what you observe here is that the red dots are associated with people who have whose health does not limit everyday activities, whereas blue dots does. Now, what you observe here, remember that we're talking about individuals who are 34 years old. For this kind of people, the notion that health does not limit everyday activities, red dots, does not have a great marginal positive effects. Whereas the contrary does a lot. The fact that, in other words, the fact that health does not limit your everyday activities is something that you assume. It's normal. You're not happy because of that. But on the other hand, if instead it does, you cannot go to groceries, to sports because you have some health issue, this can depress you a lot. And this is a kind of findings that is quite unusual It's something that linear coefficients cannot tell you, because they tell you the average marginal effect. Instead, here we are looking at each individual. Something similar, for instance, you can observe for good conduct. The red dots are associated with people that are 34 and never been to jail. The fact that you've never been to jail, this information by itself, doesn't make you any happier, because overall it's normal to have never been to jail. Whereas on the opposite hand, the fact that you have been to jail makes you a lot sadder. This only notion makes you a lot sadder. So, to sum up, some concluding remarks on the predictive accuracy issue. Given the challenges behind the predictive task, the issue of omitted variables, we don't know exactly all the predictors affecting life satisfaction, or measurement errors. People say life satisfaction in an improper manner, they not say their real value, or the issue of sample sizes and the necessity to interpret. We found that on British core study, machine learning algorithms did not lead to any major improvement in predictive accuracy. For this reason, according to Occam's razor principle, that is both a philosophical concept from the 13th century, but also a stated theorem in statistical learning theory, linear methods, simplest ones, have to be preferred. It remains to understand if this similar performance is due to actual linearities in the data, or rather to the impossibility at all of model anything beyond linear methods. Using a richer set of control, we have observed an improvement in predictive accuracy across all methods, and we are now working with colleagues from Oxford and LSE on including potentially hundreds of variables. The interesting bits are on the interpretability side. So despite incapability of improving predictive accuracy, machine learning methods has led to very interesting novel findings. Although marital status, emotional and physical health remain the most important variables as per literature, we observe that gender becomes insignificant in nonlinear analysis. Indeed, while gender, so being a woman, had the third largest absolute coefficient in linear regression standardized, it becomes only the 14th most important when we talk about permutation importance and average mean absolute SHAP values. This is in line with some novel findings. Now there is a lot of research on non-parametric methods in life satisfaction, and Oparines Risuma have found out indeed that they have a similar finding, and they find that female is negatively correlated with latent life satisfaction, whereas it's correlated positively with reported life satisfaction. In other words, what might be capturing here is that women tend to feel more stigmatized in saying that they are not actually satisfied with life. And final remark is that SHAP values, not computed in absolute values, but in the actual value, allows us to interpret at a marginal level, at an individual level, rather than on average. With this, I'm done, and I look forward to questions, comments, ideas, anything.
Thank you, Niccolo. Very nice presentation. And let me open the discussion. So everybody who wants to ask a question, just switch on your mic or webcam camera if possible, and just ask a question.
Hi, Niccolo, can you hear me?
Of course I can.
Hi, thank you very much for the presentation. I really enjoy and very interesting. Also because you know that I'm doing similar stuff. I have one question about one of the first points you mentioned about this overfitting. That basically, you say that there are two ways to reduce this overfitting. One would be increase the sample size, and the other would be try to reduce the noise in the predictor set. So since usually increasing sample size is not available, would you suggest in order to reduce this noise to perform some variable selection prior to feeding the model, and then evaluate the model after? The evaluated model will be the ones that use this shrinked predictor set, because what I'm using now is a predictor set that counts around 300 features, but of course, and I'm arriving at an accuracy of 90% in the validation sample. But then the test set, in the test set, the performance are very, very bad, in that at least at 50%. So I'm thinking to maybe perform this variable selection prior to feeding the model. But I don't know whether like is something you have seen or something you suggest. So your thought on this. Thank you.
Well, you're welcome. So it totally makes sense to perform variable selection to clean your data, engineer variables properly, because it is true that including more variables can help with the so-called irreducible error, so basically omitted variables. But if what you are including are fundamentally your variables that are explaining the same thing, are not actually adding information, all you're doing is just creating multicollinearity and noise that somehow, so additional parts of likelihood that models will tend to model, but that are actually are not adding information. So adding more variables makes sense as long as they are uncorrelated. So I would suggest you, before going for cleaning, try to see how much parametric, so direct correlation coefficient, correlation, linear correlation measures, but also non-parametric measures, Spearman rank, these kind of things, actually how correlated are the variables. If these hundreds of predictors are uncorrelated, you can keep them. But if you notice that are already correlated, I don't see the point in having them.
All right. Right. And another point, thank you very much. Another point I'm thinking about, because you said that you use 1,000 train test split, which is like higher than what is being suggested in the literature, that like you're referring to folds in that, or like so you had split in 100 folds your training sample, and you're like estimating 100 times the test error in the validation sample.
That's correct. So what I do is I create 100 training test splits, so completely 100 different splits. And then I simply run random forest on each of them. This is it. 100, not 10,000, not 100, 100. So
100, but don't you think it's very high compared to what is being suggested in the theory? Like, because they usually suggest from 5 to 10 folds.
yeah, I mean, no, just to make it clear, here we're not talking about the cross-validation process. Okay, so when it comes to cross-validation and finding the hyperparameters for the random forest, I still use 4 to 5-fold cross-validation, clearly. What I do is that this is what happens a priori. So like at the very start, I create one training set, I do the analysis, so cross-validating on that, hyperparameters, etc., done. Then new training set, cross-validating on that, hyperparameters, fitting, predicting, etc., and so far so on. So I hope this makes clear.
Mm-hmm.
Okay.
Mm-hmm.
So cross-validation is still 4 to 5-fold, something like that. Whereas it's literally different training test splits that I'm using here.
All right. All right. I get. Okay. Thank you. Thank you very much.
Welcome.
Yeah, hello. So thank you very much for a very interesting talk. And I have several questions. One is, so I like the idea. I mean, this is something that it's often not done to make the split as you did it with several individual, like let me call it the overall cross-validation. While within, as you correctly explained, within each split, you are still doing the cross-validation. I was wondering what was the time that the overall procedure took with this 100 splits?
1 month. Clearly a lot of time.
1 month, yes. That's what I was guessing. That's the cost, of course, of this precision.
Mm-hmm.
Okay. Then I was wondering, in the times as they are now, is it not a bit delicate to bring out a study where you just have 2 components for gender?
I agree with you. It's just that this is what you still have in the data. As of today, even in the last releases of SOAP, you have not yet people who don't identify as binary. I agree with you. I actually look forward to work with variables that have multiple levels, which numerically is better. So rather than dummies, yes, I look forward to it. It's a limitation that we are clearly stating in the data. In the paper, we say this is what we have in the data, and we acknowledge the future developments in on this side. I would like also, it could be particularly interesting to understand people who identify non-binary, how they report their life satisfactions. There will be studies on that. Maybe are people who spend their life being stigmatized, maybe bullied. This will open up a lot of research. I look forward to it for sure.
Okay, thank you. So I really like your description of the Shapley values, because it made it very clear also when you showed in the end that you get this individual information by the positive and negative, which clearly is an added value as with respect to the classical feature importance, definitely. I was wondering if you would also, if you had not taken a look at the so-called partial dependence plots.
Yes, it's something that I was going to look out. The point is that in the paper, we already have a lot of findings, as you have imagined. So we had to make a bit of a choice, and I decided to not include them. But
because I was actually wondering, so also working in interpretable machine learning, I'm wondering how far can one not say that the Shapley values with this type of plot can be equivalent to the combination of partial dependence plots and feature importance? Do you have any take on that?
Feature importance, you mean the measure?
For me, this is the feature importance with the permutation. Yes. So this
with permutation, okay.
Yeah. So this one combined with partial dependence plots, I wonder in how far this would contain different or more information than the Shapley values, as the Shapley values already give also somehow, information on how each individual feature acts on the outcome.
It's a good point. In the very end, I think, like already if you think of the ranking that you see here, so it's overall like these are only the 15 for a matter of space. But if you see this ranking, keep in mind like maybe the first 5, and you see what we have here overall are similar. This is because when I say that we are including or not a variable in a coalition, so the term in square brackets, the variable is excluded from the coalition via permutation. So two measures still are clearly related, and probably adding partial dependent plots will lead to similar results. The thing is, I think that Shapley values, the good thing of partial dependence plots is that they still try to capture a bit more the interactions about variables. So this could be a added value. But in general, I find this graph here already being, the idea is that anyway, we want to find new insights with respect to a linear regression coefficients. And when you estimate a coefficient for log income, 0.7, you apply this coefficient like indiscriminately to extremely poor people and extremely wealthy people. Here, no. Here you have a marginal effect of income for poor people and for rich people. So I think already this graph here, for me, this is the bit that summarizes the most the point. So this is why I think that I would not say the adding partial dependent plots with permutation importance would be superfluous, but probably will lead to the same findings we have here.
Okay, thank you very much. Just a very last short question, then I'm leaving the discussion for now. Is so as a statistician, of course, I am jumping on words that I see where I see significance. So when you said in your, I think last or second last slide, you said that a gender becomes insignificant. Is this really insignificant in the sense of statistical significance, or is it just an abuse of language?
Let's say that is an abuse of notation, because here I don't have like a proper test of hypothesis, a p-value. So I say it's just basically insignificance, more in the literal. Yes, probably this is a term I should be careful of. Let's say I should use unimportant. It's better. It's a good catch. Thank you.
Yeah, I wanted to say, I would suggest that.
Yeah, no, for sure. Significant is a dangerous word. I will use unimportant. Here is used more in a less statistical, more I can say literal sense.
Okay, great. Well, thank you very much again.
Thank you, Christoph.
I have a comment. Somehow the topic of this interpretability bring to my mind the presentation of Margarita Alexandrova, the second series of lecture. and I think she's here with us today, on causality. I mean, you have the correlation, but we don't know anything about what causes what, whether the let's say well-being it is correlated with, let's say, healthy style of life, but the question is whether which causes which behavior. Like if you feel good, that you also have, let's say, time and motivation to do some physical activities, but it can be vice versa. If you do physical activities, you feel good. So I don't know, maybe Margarita can sneak in a word. Maybe she has some more ideas.
I have. Hello, thank you. So I had some similar thoughts, but I know people from humanities, they work a lot of causality. Maybe this analysis was already done. But when the variables were presented, I was wondering, for example, the impact of marital status on the happiness. Yeah, it might be inverse. Maybe it's inverse, that the people who are happier, they build healthy relationships and then they stay married or in couple. So do you study any of such questions? Which variables are the causal and the effect?
So in this particular study, no, we do not make like proper causal studies, like using techniques, particular causal inference techniques. We rely here on the literature. So the literature argues that marital status causes life satisfaction rather than the point is, if you think at how the question is put, like if you think you are going to say that you're satisfied or not, this is an internal state that is influenced by something else. It's not, there is some literature on how you start, happiness is something you find inside, but still it remains like, here there are not formal, in this paper, let's say, formal studies and analysis of causality, but there is in literature, and in general, if you think, like, if you say that you're satisfied or not, immediately you will think that you're, in general, your life, and depending on the characteristics, the situation in which you are, you will then give a reply. This is fundamentally the argument there is. If your question is about some technical analysis of causality, the answer is no, there isn't here in this work.
Okay, thank you.
You're welcome. Thank you.
And also, may I have a question about this, the treatment of overfitting? Again, it somehow relates to what one of the earlier questions were. So you mentioned that let's say there are two methods, like simplifying the model. Let's say the index real case, you have a linear relationship, or increase the data sets in order to have evidence about yeah. And then maybe, do you know any other model methods to how treat the problem of overfitting, like inducing or introducing stochasticity to your model, just to get rid of this overfitting that is caused by noise in the data?
Yes, for sure, using penalization, like whether it is weight decay neural networks or simple penalization linear models. I think this is, in general, it's correct, sure, that's a way to reduce overfitting. I think this is, in general, what is already here said in the phrase, we can use less expressive models with fewer parameters. For instance, if you think a dropout in neural networks, this basically means that some of the neurons are ignored, randomly ignored, and this is a way to say using fewer parameters. Or in more simple, in a penalized linear regression, lasso shrinks some variables. This is penalization, what you were referring, but it's encompassing in using a model with fewer parameters because some of the variables are shrunk. So what you're saying is surely correct. I think is already embedded, let's say, in the using in the expression here, we can use less expressive models with fewer parameters.
Okay, I see. Thank you for
You're welcome. Thank you.
Answer. All right. So if there is no more question in the the audience, let me thank you again, and Niccolo for a nice presentation, and all of you for your attention and for the discussion. The talk has been recorded, so I think everybody can get back to it and contact Niccolo if they have further questions in the future or ideas. Thank you so much. Have a good day, and let me invite you for the next week seminar, same time.
Thank you. Goodbye.